Okay, welcome back to the class. So, in the following slide, I will introduce the differential form of the continuity. Okay, so before that, we go back to see what our continuity equations is the MCV change with the time, and maybe we plus the mass rate for the outflow and the minus the mass rate for the inflow, and will equal to 0. Okay, so what is the differential form? So right now we are looking for the target change to the small fluid particle. Okay, so we only change to our target is the small fluid particle. As you can see, the card figure showing here, we only have the qubit, and the fluid particle is the cubic particle, and we just a larger view for a small fluid particle. So you can see to the right hand side the carbon field in here, and then we have the defined the directions is the right hand side is the x directions, and here is the y directions, and the upper positive upper is the z directions. So in that the definition for the directions, so we have the velocity u in right hand side. Okay, we have the velocity u to right, and the v velocity and the w. Okay, and the qubit of the length along the x directions, we have the delta x, and along the y direction we have delta y, and the z directions we have the delta z. Okay, so after we only focus on the target of the small qubit fluid particles, and then we first focus on the problems in the z-x plane. So we only focus on the z-x plane, and we assume that the density is the constant values for this problem. Okay, so what's the problem we have in here? This is our inflow, and there is our outflow. Okay, so we have the inflow in here, and this is our outflow. So the dashed line in here is our control surface. So the idea is this is our point. So we have a point O in here, and we assume the point O in here with the velocity multiplied the density is rho u. And we have another point on the right hand is our point related to the outflow. And we actually know the distance between 2 points is 2 over delta t, right? 2 over delta t. So how large velocity multiply rho in here on the right hand side? So the right hand side, as we know, there's the outflow point. Okay, so we still have a rho u, and we apply the Taylor expansions. So we know that we assume the point left to the point right, the velocity changes, the gradient is a linear gradient. So we have a rho, the rho u dt is a linear gradient relationship, and multiply the distance changes is 2 over delta x. But based on the Tyler expansions, we know that we still have some higher order terms, but we can assume the 2 over delta x is quite smaller, so we can ignore the higher order mode. Okay, and you can similar, you can put another point to the left hand side, and this point we also know that is the inflow point, and the distance changes between 2 points, also the 2 over delta x. Okay, so the velocity in the inflow side we can write to be the rho u minus the rho u dx and multiply the 2 over delta x. And why we use the minus? The minus symbol because we assume the linear gradient of the velocity along the x is the positive. So when we go the left, so the distance is decreased. So we use the minus in here. So right now we can calculate the mass rate because we have the rho u values. So the mass rate, we know that for the outflow, this is for the outflow, so it's equal to rho u plus the rho u dx multiply the 2 over delta x, and we need to multiply the cross-section area. It's because we focus on the dx plane, so the cross-section area is delta y multiplied delta z. Okay, and then we can calculate the rho inflow rate. Okay, and this will equal to rho u minus rho u rho x 2 over delta x multiply the dy dz. Okay, so we know that the total mass rate along the inflow and the outflow when we focus on the zx plane will equal to the m out minus the m rate inflow. Okay, so you can the outflow minus the inflow. So finally, you only have rho u rho x and the delta x, delta y, and the delta z. Okay, so and this is the patterns are summarized on the right hand side. So you have the final is d rho u dx multiply the delta x, delta y, delta z. Okay, so this is the first the mass flow rate along the x directions. So we can similar to write down the mass flow rate changes along the y direction will be to the rho v and the dy and the dx delta x dy and the dz, and along the z directions can be rewrite by the rho w and the dz and the delta x, delta y, and the delta z. Okay, so we can sum all of the mass flow rate changes contributed by the different directions. So we can summarize all the d rho u dx plus the d rho v dy and the plus d rho w dz and multiply the delta x, delta y, and the delta z. Okay, And then the next we are trying to focus on the items for this. The MCV change with the time, because the previous slide we already got the formula for the delta M rate, right? So actually the MCV, you can discuss stuff from the MCV, because the MCV is the mass in the qubit fluid particle. And because the particle is a qubit, so we know that the volumes for the qubit particle is dx, dy, and dz. This is the volumes. And the volumes multiply the density. So we know that this is the MCV. So if we calculate the MCV dt, we know that will equal to the d and the dt. The inside is delta x, delta y, and the delta z, and keep the density plus the d plus we keep the delta x, delta y, and delta z, and multiply the d rho dt, right? Okay. And we know that the qubit particle, the volumes cannot change with the time, so we don't have this item. So the MCV dt, finally we only have the delta x, delta y, and delta z, d rho dt, right? So you can put all of the information, go back to the continuity equations. So the d rho dt multiply the delta x, delta y, and delta z. This item is for the MCV dt. Will plus the d rho u dx plus the d rho v dy plus d rho w dz, and the delta x, delta y, and delta z will equal to 0. So we can cancel out all of the qubit volumes in here. So we rewrite the final continuity for a differential form in here. And we know that the second items can also be rewrite to the differential operators dot product with the low v vectors. Okay, dot product for the low v vectors. Okay, so this is the final general formula for the differential form of the continuity. Okay, so right now we consider some different conditions to better understand how can we apply the differential form of the continuity to real case. So the first assumptions we think our flow is if satisfy the steady flow. So we know that the density cannot be changed with the time difference. So we don't have the d rho dt items will equal to the 0 in here. And the second, we consider the incompressible flow. So that indicates the rho is the constant value at the different spatial locations. So finally, we only have the continuity equations. We only have the item to be the great differential operator dot product with the velocity factors will equal to 0. So this is a divergence of the velocity field is equal 0. Okay, so what is the idea? We can expand the divergence in here that indicate the du dx plus the dv dy will equal 0. So that means the u velocities change with along the x directions plus the v velocity change with the y directions will equal 0. So on the bottom you can see if we focus on the velocity in here, so the u velocity initially is larger, and then the u velocity to the right hand side to be the minus, because the velocity u along the x direction is decreased. So we have the minus in here, and if we focus on the y velocity v, so the initially v velocity is smaller, and then go to the right hand side, the v velocity is increased along the y directions. So that indicates that the item in here is the positive. So 1 minus and 1 positive finally equal to 0 values. So that means the divergence of the velocity field is equal to 0 can help us to better understand the velocity field, because all of the velocity fields satisfy the condition of the steady flow and the incompressible flow. The divergence of the velocity is always equal to 0. So if you can try to rethink, we have teach you additional parameter is we do the cross product with the velocity field will equal to 0. That indicates the flow is rotational flow, right? So different conditions, we can have a different velocities properties, but all of the properties, all of the formulas showing here just try to help us to better understand the velocity field. Okay, so right now we have the one exercise, and we can try to practice how can we apply the continuity for the differential form. So as you can see, the questions exercise we satisfy our problem is satisfy the incompressible flow and the steady flow. So we know that the divergence of the velocity field is equal to 0. And because our questions is 2D flow, so we know that the we have the du and the dx plus the dv dy will equal to the 0, right? And then we only have the u velocity is as function of the xy is equal to the minus x and y u. And we have the boundary conditions. We know that the v velocity any x location but the y equal to 1, the v velocity will equal to 0. So the problem is what is the v velocity functions? Okay, so we can put the all of we know inside the formulas. So the dx and the u in here is the minus x divided y, and the u constant values plus the dv dy will equal to 0, right? So this function, we take the differential, that will equal to the minus u divided y and plus the dv dy will equal 0. So that's the dv dy is equal to the u and the y. So we have the dv and will equal to the u y dy, and we do the integration. Okay, and after we do the integrations, okay, so that we'll have the maybe have the f(x) functions plus the constant value in here. So the final v function x, y will equal to the u and the long y plus the f(x) plus the constant value. So right now we can put the boundary condition inside the equations. The boundary condition, we know that the v for any x location but the y equal to 1 will equal to 0. So you put it inside, you will know that the x function plus the constant is equal to 0. Okay, so finally v velocity as function of the xy will equal to u long y. Okay, so this is our final solutions. So the idea is, because we know that the flow condition satisfy the incompressible and the steady flow, so based on the differential form of the continuity equations, we know that the divergence of the velocity field is equal to 0. So we can have the government equation du dx plus the dv dy will always equal to 0. And we have already know the velocity along the x directions u, and then we can go back to solve the u velocity. Okay, so this is very useful when we apply the continuity equation of the differential form. So the next one, we go back to discuss with the stream function and the potential functions. In the previous chapter 4, I have very quickly introduced the stream functions, and we know that the stream functions, maybe a different field we have a different stream function, but if we pick up the one point and we take the tangent directions, we know that the velocity at this red point with the magnitude and the directions. Okay, so that indicates the stream function can be applied to describe the velocity field, especially for the flow magnitude and the flow directions. So as a sentence shown here, the stream function can be used to plot the straight lines of the flow and find the flow properties. Okay, so under considerations of the 2D flow, and the velocity components can be calculated in xy coordinate. So we define the u is the first we define the u. Sorry, I changed the pen size. So the u is the minus d per c dy, and the v velocity is the d per c and dx. So if we have known the conditions, the flow is the irrotational flow. The flow is the irrotational flow. So, and we know that the irrotational flow satisfy the differential operators cross product with the velocity vector will equal to 0. And then we know that, so we can write down the dv dx minus the du dy will equal 0, right? And so, and we can put the definitions of the u and the v inside the the equation in here. So dx, the v velocity in here is d per c dx, and then minus dy, but the u velocity in here is the minus d per c and dy will equal 0. So that indicates the dx squared d per c squared plus the d per c squared dy squared will always equal to 0. And we call that is the Laplace equation for the straight line per c. Okay, but this is the relations especially satisfied for the irrotational flow. Okay, and the next is we first introduce the potential function phi, and actually the potential function will be perpendicular to the string functions, and the gradient of the potential functions is proportional to the velocity speed. So for the potential function, we define new parameters per c. Phi is u is equal to the d phi dx, and the v velocity is equal to the dy and dy. And we apply the differential form of the continuity for the incompressible flow. So this is right now our conditions. So that means the flow field is satisfied, the divergence is equal to 0. So we have the du dx plus the dv dy will equal to 0. So we put the velocity defined it by the phi functions. So the u is equal to the dy dx, and the plus the dy, and the v velocity is dy dy equal to 0. So we can rewrite to the formula to be the d square phi square dx square plus the dy dy square is equal to 0. So in that equation, we call that is the Laplace equation for the potential function phi. Okay, so you can see the blue color in here is our straight line, for one straight line for the constant c values, and another is our potential functions. And you see the potential function and the string function are always perpendicular each others. Okay, so we have the final exercise in here. We have the current flow conditions, and we are trying to find out the straight line for these problems. Okay, what are string functions of the current flow? Okay, so we first write down the velocity profile of the current flow is the uy is equal to the u multiplied the y and divided the L. Okay, so because we have discussed for the current flow, and we have a certain definition, we know that the u is equal to the minus d per c and dy. Okay, and v is equal to the d per c and dx. And then for a current flow, we don't have the v velocity first. Okay, so we know that we don't have a v velocity is equal to 0. So that means that the per c dx is equal to 0. Okay, so maybe per c functions of the x and y is the maybe it's the g y function and the plus the one constant. Okay, because the gy function differential with the x is equal to 0, and the constant value also have the differential value is 0. Okay, and the second condition, we know that the u is equal to the minus d per c and dy. Okay, and we have the u functions already, so the u and the y divided the L is equal to the d minus d per c dy. Okay, so we can rewrite the equation. We know that the d per c, maybe I use the positive, d per c is equal to the minus and the u divided L multiply y and dy. So we can do the integrations both sides, and the u divided L is constant, so I put outside of the integration operator. So we know that the y xy will equal to the 2L minus u y squared, and then we may have the f x, and we have the maybe an additional constant value. So we can compare two equations. This is equation 1. This is equation 2. Okay, you compare each side. You may know that finally the per c xy is only equal to the minus u to L and the y squared. Okay, and you can decide that different conditions have different streamline functions. Okay, so this is our streamline functions. Okay, and in others, as you can as you remember, in the chapter 4, I also teach you how can we determine the streamline function. How can we determine the streamline function? Another way, we know that the u the x dy will equal to the u velocity divided the 0, right? The divided the 0. So you can divided the velocity v. So you know that the v dx will equal to the u dy. And then you can take the integrations both sides. Okay, but the left hand side, we don't have the v velocity, so you know that the u dy integration will equal to 0. Okay, so you already have the u velocity function is u y divided L and the dy, and you can do the integration will equal to 2L u y squared, and the plus the c will equal to 0. Okay, so we can define the stream functions. The stream functions of the x and the y is always equal to the uy squared divided to L, and then that will equal to the minus constant values. So the different constant value in here, you will have the different streamline functions. Okay, so in this chapter 5, I teach you how can we determine the stream function by the certain definition is the u is equal to the minus d per c dy, and the v velocity is the d per c dx. Okay, so today we finish the chapter 5. So the next class on Wednesday, we will move to our topic to the chapter 6. So we are wondering to discuss the physical property of the momentum changes along the control surface boundary, and how change the momentums inside the control volume problems. And we will have the quiz on the Wednesday. So see you on Wednesday.